with the generator differential protection, and also in the afternoon for the line differential protection. So without further ado, I would like to call upon our speaker, Mr. Uttam Mishra.
Thank you. Good morning, everyone.
Morning.
So today we are going to learn generator differential protection. It is differential protection is same, almost same for transformer, generator, line, as well as bus bar. So the basic concept of differential is same as we learned yesterday. So in generator differential, there are many differential protections depending on the generating station. Like a steam thermal power plant, you will see there are 4 5 differential protection if plant is big. And if it is a hydro power plant, there is a different differential protections are used. The concept of all the differential is same. So as yesterday it is explained in detail all the part of differential. So we will be covering today whatever part left yesterday, so that it will be a complete protection training. So not only for transformer differential, but all type of protection. So in generating station, one dedicated generator protection is there. Other are auxiliary transformer protections. Also overall differential protection, which cover differential generator as well as the generating transformer in one part. So these are the few differences. Otherwise, the concept is same. So we will be learning the mm, from beginning again, not in detail like yesterday. As we know, you are already done that part. So we have. Oh, wait. Okay, this slide you understand well. I think I'll just go through quickly. This one is the operating coil of differential. If internal fault is there, then the current will go through the differential coil. If it is external fault, then I have taken the ratio 1:1 to understand it well. If it is through fall, then current will circulate, but there is no current in differential coil, so the relay will not operate. These all are for the ideal condition. Uh, Now the ratio is different. Then what happens? Then we need a compensation. So earlier we used to do the through seating. Earlier we used to do the compensation matching the CT. Now numerical relays have all options. Everything will be taken care by the numerical relay itself. So we do not require now these CTs. So here we will start actually. So yesterday there was a question why these slopes are there. So what will be if we have only differential uh, setting, only not slope setting, then how the relay will react? That is what we learned. So what we have seen in the previous slides, that are all are ideal conditions, but in actual the relay will behave differently based because there are different errors in the uh, during the actual operation. What are that errors? CT errors. So both CT will inject current and there will be some difference. The, whatever the perfect design, but still there will be some error. If we take the ideal condition, zero current in the differential coil, that happen only conceptually, but not actually. Due to this CT error, some current will flow through the differential coil. Uh, Relay errors, some measurement errors in the relay. So there will be some difference in that. Mismatch in the CT ratio and relay taps. If it is electromechanical relay, so there will be these relay tap errors. Like yesterday explained how we compensate that through the taps. So relay taps is for electromechanical relay only. So CT ratios, mismatch in CT ratio. Suppose we have 600, 1600 CT ratio for different side. So relay will compensate it through the matching factor, but still there will be some errors. And this is the main cause of current difference, tap changer. If it is the at normal tap, then the error will be less. But suppose system requirement is to change the tap. So when we change the tap, we are not going to change the relay setting every time. So we should compensate this in our differential relay. So when we change the tap through OLTC, then the differential current will increase in that case. So it should be compensated in our relay setting. Transformer normal magnetizing current. When we charge the transformer, we learn a lot of things yesterday. While charging the transformer, there is a heavy current flow for 3-4 cycle. So due to that, differential may operate. So how we compensate, we learned yesterday. And these these are the one part. This one is the other part. These these factors create more difference in the relays. So that is why it is in two different colors. So CT saturation, energy inrush, energizing inrush, sympathetic and recovery inrush, over excitation. So these are the factors which affect more. So if we see, then these error create around 20% to 35% error in the differential current. So these are the first slope what we consider. That is why, because the 20 to 35% error. That is why our slope is around 20 to 30% generally we consider. So based on different transformer, sometimes you will see that the setting might be 0.4 as well. So general setting we do 0.2 to 0.3. So but generally these are field experience, based on that we do this setting. And the second one create more errors. It is around 40%. So that is why the second slope is at a higher side. So now I think you have idea why we have three slopes. So you can see it graphically as well. So for first step we have magnetizing current. This is a full load boundary. So whatever we mentioned in earlier slide, you can see here. So CT relay tap mismatch, CT errors, tap changer errors. So due to this, suppose I set this I pickup value, only this setting is there, then you can see during starting, due to inrush it may trip, due to tap changer it may trip. So it is going above the our setting. So that is why we require two way we can do. Either we can increase the pickup value, but still it will not solve our problem, because up to full load current it is okay, but for the through fault currents it may maloperate again. So that is why we have to implement slope. Till now we have considered only the first factors. There was two parts in my previous slide. If this first part was having around 20 to 35% error, so why we are considering only 0.2 sometimes or 0.3? Because now electromechanical relay is not there. So due to the tab setting, there was more error is there. But now in numerical relay, this error is reduced. That is why, so this error reduced, so our setting can also be decreased. That is why sometimes we use 0.2 or 0.3 based on the system. If there is no tap changer, or we do not have requirement of tap change, so the error may reduce more. So in that case 0.2 will be perfectly okay, and slope can also be 20% instead of 30%. Okay. So this is based on the our system we select slightly, but here we have considered all errors which can be in the system. Okay. So why we take slope? I think it is first slope. It is clear now. If anyone has any question, you can ask. Now we have a slope, so we can reduce the pickup setting also, because all other error will be compensated through the slope. So we do not need higher pickup value. So our protection system will work more effectively using this.
Sir, excuse me, sir. sets the slopes wrongly or not too accurate, follows this all these errors.
Mm.
So the pickups will have every time we energize after shutdown, this pickup for relays pickup. So without doing anything on the relays, can we keep energizing until it turns on transformer?
Yeah,
It
when we
happens 2 3 times or 4 times at times. We keep energizing normalize the system back.
no, not like that. If you are energizing and relay is tripping,
Yes.
that means there is some setting. You should first analyze the fault DR. If any case differential is tripping, if it is the first charging, then that means there is a problem in the your setting. So you should analyze that from fault DR. You can easily analyze how much current and what factor need the differential relay to operate. So you can easily find out with the modern relays. So you do not just blindly try to charge the transformer. It may damage your transformer. So without knowing the reason why it is tripping, you should not charge it again and again. And most common thing what I have seen, as you are saying that when we are charging, the transformer is tripping. So mostly I have seen it is due to harmonic current is not many. So sometimes we have harmonic blocking in the differential protection, but in SEF also, SEF relay, if you have enabled the SEF protection, so during charging, due to neutral current will flow. During charging, it will not that all three phase current have equal current, equal charging current, magnetizing current. So there will be unbalance, and suppose it is your setting is less in the SEF, that may cause the tripping. So that is why many do the harmonic blocking in that case also. So these are the few factors which can trip the transformer during charging.
SEF is standby fault.
SEF is it is just like earth fault. So it is connected in a neutral. So
Normal fault.
yeah. So apart from the REF and differential, the SEF is another protection, which is unbalanced current measure in neutral.
But in my case, when you energize the transformer,
Mm.
you enable the harmonic blocking, differential didn't trip, but it trip on standby fault or other fault.
Mm.
Suppose harmonic blocking also block all those fault features, right?
No, no.
No.
So if you see in the settings, in overcurrent also in the SEF also there is harmonic blocking option. Almost in all relay, maybe if it is a mm, 33 kV or lower system, then it may not be. But mostly I have seen there is also this system to block the harmonic. In ABB, all is even small relays, this function is there. And mostly, if it is a transformer, so it is mostly enabled, so that it can not cause maloperations. Many times, especially I have seen these problems in the solar plants in India. There are many solar plants and not very compatible engineers. So I have tie up with those companies. So whenever there is a problem, they contact me. Then I have seen this problem many times. There are setting problems. So if your transformer is tripping, so that means there is a problem in the setting. Every time this is happening, or so you should analyze that why it is tripping and correct your setting according to that.
The reason why I'm asking because
Yeah.
because we are from end user side, we are on the tester side only. So for us to understand this, even having some,
Yeah, you can ask
yeah, that's the
whatever
reason.
you have. You came here to
It may sound stupid for someone else, but then,
and
Yeah.
never hesitate to ask.
yeah,
So every question is an important question. So if you are asking, many other have also the same question.
yeah, maybe.
Okay, so this first slope is clear, I think. So second is the external fault, CT saturation. So you can see that if we have only one slope, then during external fault or CT saturation case, this point may move here. So this may cause tripping again. That is why we we have to set another slope. So these factors create more errors. That is why slope is higher. So it is around 40% error. So we add a 40% in that, 30%. So it is around 70 to 80%. That is why our second slope is generally 70 to 80%. Sometimes it is 100% also. In generator, we do 150% or 120%. Why? Why in generator we do 150% and only one slope is there? Because in generator, this tap changer will not be there. CT is also almost same. There is option to. There will be some error still, but the major factor is this tap changer. So this create more error. So tap changer is not in generator. So that is why this slope may be removed and we have only one slope. So that is why in generator you will see that pickup current is up to full load or 1.2, 120% of load. After that, the second slope start due to the fault level will be higher at generator level. That is why this may create more error than transformer. So that is why this slope is instead of 70%, they put it to 120 to 150%. Okay. And this slope requirement is not in generator. That is why. Okay. So now, yesterday your question was why we add restraint. So till now we have seen that it is unbalanced current which is flowing through this differential coil, and due to which differential protection is operating. So as we seen last slide, there are slopes. So how we can create slope? If we have just differential setting, so we cannot create slope. So we require some reference. Based on that, we can add the slope. So what happened when the same thing? So here also it is inside. So a restraining coil added here. So what we are doing, we are measuring this restraint current, and based on that we are plotting the graph. If restraint current is this one, then relay should operate that way at that slope. If restraint current is increased more, then the slope should be 70% or 80%. So if suppose we have only one coil, then we can measure this current only. So only we have control that differential current, we can increase or decrease, like we are moving the pickup point. So we are increasing the pickup setting. But if we require that slope, then we require restraining coil, which can measure the current, and based on that take decision. So like you have already seen the slope. So okay. This restraining coil is in every relay, but measuring technique is different in all relays. So it is not a standard that if at this current the that differential will slope at this differential slope should be 30% or 40%. What we have explained, that is just errors, how much error it create. So the slope sometimes depend on the relay setting of the particular manufacturer. All manufacturer have a different restraining current calculation method. So based on that, the relay setting system. So suppose here transformer is running at normal load, full load. Then what happened? The one, and this is, I have taken a standard 1. So suppose there is some mismatch, so it is 0.9. So 0.1 difference is there, and here you may take yesterday's calculation what we did. It was 1. Okay. So it was 1.5. So here in this yesterday's relay, the restraining current is R1 plus R2, IR1 plus IR2. Suppose in this case it will be 1.9. So it is gone to the slope, this slope more than 1. This is bias current. This is differential. So if bias current, you can see these bias current in the measurement of the any relay. So you need not to calculate it. You just inject the current in both sides, and you can see how much restraint current is there. By formula also you can calculate. So in this case it is 1.9. So it means it is going to the at slope 3, I think. If it is 1.5. Okay. So slope 3. So here the differential current should be this. So it is just for explanation. It is a vector. Sometimes it's done. So there may be not exactly same calculation. So better way you can measure in the relay measurement how much restraining current and differential current is there. So in this case, it is required. If there was no restraining coil, then at this the differential relay may not may have tripped. May have tripped. Due to this restraining coil, relay is not tripping. So and it is following this slope. So this way we calculate like we did the differential characteristic test yesterday. So through the template, if suppose we do not have any template, then also you can test manually. Okay, how the same formula what he has explained yesterday. So we will inject the current from both sides and maybe full load current. Okay, and we increase one side. So when we suppose increasing here, then what will happen due to unbalance? This differential current will keep on increasing. Okay, so only thing we have to keep in mind during manual testing. So we should follow this where the I bias is starting at which I bias, which slope is being followed. So suppose we want to test this slope, then our bias current should be between 1 to 1.5. Okay, so we will take 2 point, 1 point here, 1 point here. How we can take it? You just increase the one side current, and when differential trip, then stop and note down the both side current what you have injected. So again inject the same current and hold that value and measure the I, IR and ID value. Okay, so suppose we have this one. This one is ID one. Just what any, I will show you one actual testing example also. Just for ID one at here, and this will be IR1. Okay. Again, this point it will be IR2, ID2. The same way we had calculated the settings, we can calculate live in the relay also. We note down this one, and for slope, it is following the slope or not. If you want to calculate that, then ID2 minus ID1 divided by IR2 minus IR1. It is equal to M. Slope K or M, whatever you can say. It is this is how you calculated yesterday the settings. The same way you can inject, and these value you can read in the relay and calculate the slope. Similarly, if your I bias, if you will keep I bias more than 1.5, then you can have a 2 point here. Any point. It is not that you need an end point. Any 2 point slope will be the same. So any 2 point you calculate, and the same way second slope you can verify. If you do not have template, so easily you can test the differential relay. And this is the universal method. So any relay do not require template or zero sequence. Anything you do not need to keep in mind when you are testing this way. Okay.
You inject that you inject current side one
Mm.
and side two.
Mm.
You increase one side
Mm.
and you go to digital display and search for IDIF and
Yes.
IR and
Yes.
then do another test calculate by this formula.
Yeah, maybe suppose for this is one, so we will inject start from one itself. Okay, I bias one. We will start from one. When we increase the any side, then obviously I bias will increase. So this value is going above this one. So this will, if we are increasing one side, then it will not move like that. It will remain at one. It will move like this. Okay. So maybe here it will, the first point will be there. So we can start injecting the second point from 1.25 times. So the point will be different, but only you need to keep in the mind when you are reading the ID and I differential value, then you should take care that it is not starting at slope 2. Because if your I bias is more than 1.5, that means it is slope 3. So you can easily find out from the measurement. So once it is there, and suppose you want to keep the I bias constant, then how can you do?
This
IDIF, how you will increase IDIF? So you have option either one side increase or decrease. So if you are increasing one side, then obviously this will keep on increasing.
one reduce one increase.
Yes. So if you want to keep it constant, then one side increase, one side decrease. Differential will be keep on increasing, and I bias will be constant. So suppose this margin is very less like yesterday's setting. So in that case, you cannot find 2 point. In that case, you can follow this method. So that the I bias will be constant and differential current may be increased. So our aim is to find this point when the relay trip. At that point, what is I bias, what is I differential. 2 points we will get, then we can calculate the slope. In this way, you do not require any template. Any questions? So I explain the easiest method first, because we are moving towards more complex thing if you are creating the template. Okay, so this is already done. So differential restraint characteristic we already. So there are different formula. You can see it depends on the manufacturer. We discussed it yesterday. So this IR1 plus IR2, like we calculated it for Siemens relay as well as SEL relay yesterday. Same formula. This one is in the G Mycom series. This one is a ABB and GT60 relays. So there might be any other formula also. It is not fixed. We just need to uh, compensate that errors what we discussed. The algorithm may be different, but ultimately the concept is same. you can see differential current is the sum of all currents, vector sum, and this one is bias calculation as we see. So it is different for different relays. That is what has shown here. So this is the slope calculation method, differential operating current, restraint current. With this formula only we have calculated this manually. So only you have to keep in this mind that this is the formula for any slope calculation. And the how restraint current is different for various relays. How what happen if we use one template in other relay? You can see from the next slide. So this is the formula. Suppose we have a MICOM relay, and its formula is this one, and the setting of the slope is 25%. If we are using another relay with this formula, then what will happen? So suppose the restraint current is here in this, then it will move. At this slope, it will trip at, because here it was at 8. So at this I restraint formula, this will be here. Okay. So that is why this restraining formula affect. And sometimes if you see the suppose there are two transformers, same rating, and everything is same. If different make relay is there, then slope might be different. That is due to these I restraint formula. So it is not like if it is 30% in this relay, then other relay also should have that same. So it depends on the formula. Any question till now? Let us. Here you can easily calculate also. So it is 25%, it is by 2, then obviously this one will be half of it. So it is 12.5%. If it is 25, then it is 12.5%. Or what are other concerns? So we also discussed it yesterday. Like star delta. Yesterday it was explained very well with the formula and calculation. So I'm not going to read it. This S3 factor, delta connection S3 factor. Actually, this was also explained yesterday in voltage. The same way we can calculate in the current also. When we are moving from star to delta, then there is a √3 factor is added. So you can see in the now these are the basic things. There are some more things we will see in detail in the coming slide. But this is a generator protection, generator differential protection system. So what are difference between the normal differential, transformer differential and generator differential? We can see here. So these are the thermal plant scheme. It is just for example, different plant has different arrangement, but these are the general arrangement what we can see. So in thermal plant, you can see generator is there, and in this plant, one differential protection will be here, 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 and combining all, there is a overall differential protection. So if it is a big plant, then for one unit only, you might have 5 differential protection. So if it is only generator protection, that is it is the simplest one. If it is other product, suppose it is overall differential protection. So it is winding wise, these settings will be different. Setting will be same, but calculation method will be same. But the based on maybe this is a delta star, star delta, whatever combination. So rating is different. So these rating will be different. So based on that, we can have that calculation of the differential protection. If it is an individual protection, then it is easy, as we are doing the differential protection, that will be applicable to all. This is the same transformer what we are tested earlier. So the protection will be also same, not different. So in generator protection, there are many protections. You can see in the next slide. So one of them is only generator differential. So that is why what we learn in the transformer differential protection, that all are applicable to generator differential also. And it has only one slope. Why it has only one slope, we already discussed. And what is difference between this and this? So gas and pumped storage plant, uh, uh, these plants generally continuously run. These plants we generally use as a backup. Not every time it run, and it work in pump mode also. So this generator may work differently. That is why sometimes there is it may operate differential protection. So that is why these two plants have a different differential schemes. The basic concept is same, but to block the differential protection during the generator running, so there is a scheme followed in different plants. We will see in the coming slide. This is a typical generator protections. You can see there are 25 to 30 protection, different protection in the generators. So we are here discussing only the differential protection. So we're not going to all protection in detail. So here you can see this is a 87G generator protection. This is transformer protection. This is a auxiliary transformer protections. So here only one, but it might be two or three also. Depends on the power plant. So how generator differential work in this? The protected zone will be between neutral and terminal CT. And in generator protection, this is the concern. So it do not detect earth fault reliably. Why? Because generator neutral is grounded through the NGT, so there are a lot of impedance. So the differential current, earth fault current do not flow so easily like in the transformer differential. That is why mostly these differential relay also work for the face-to-face type of faults. Maybe sometimes earth fault during face-to-ground fault, maybe if it is not much current, then differential current may not detect. So that is why we have additional protections, stator protection for 95% and 0 to 5%. Additional protections are especially for earth fault conditions. So these differential work very well for face-to-face faults, but for during earth fault, we have multiple protection in generator.
Dedicated function required.
Hmm?
Dedicated function required.
Yeah, dedicated function required. That is what I said. 0 to 95%. Yesterday he has explained REF protection. So that additional protection is in generator. That is why there are many protection in generator. Here you can see neutral displacement, and this is a REF. So that all additional functions are there in this. So it is not like that it will never detect, but due to these ground, if earth fault current will not flow, then how it can detect. So, but these are the system which can effectively detect all these conditions. So last time when we did, we had discussed all these protections in slightly detail, not much detail, but at least what are these functions, and what are how we test this, and how we can detect the different type of fault. So we discussed it last time. So right now you just understand the reason why it is there. You why this line is written. You can understand because of the uh, ground impedance. In the transformer case, it is solidly grounded, so earth fault condition will be detected very easily. So if differential relay is operating, then what condition it will be there? All CV will be tripped, excitation, turbine, stator, everything is because differential is main protection. And as I said, there is only one slope in this, and this slope depends on the manufacturer recommendation. We cannot set ourselves. We should read the generator specification, operating curve. Based on that, we decide this slope. So it may be 120 to 150%. So, and second slope is not there, as we uh, do not have a tap changer and all these things. Here slope 25 to 80%, but it is just one setting. So it may be generally what I have seen. I have written this one. It is not, exactly. So generally I have seen this slope is from 80% to 150%, not 25%. I can modify this. So the second condition, so that was the thermal power plant. Here there is during a starting, they are in pump mode. The main generator will pick up. So here you can see static frequency converter. So during starting the power will be fed through this, and in this case, because the current is different and it is also connected to the other thing, then this differential may operate during starting in these conditions. That is why there is a during the rotor acceleration, so static frequency converter which is connected here. So this current will create a fault condition in this case. That is why there is option. This is blocking options. It is just an example. Different blocking options implemented in the relay, so that during the pump mode, this isolator may change and the differential protection blocked in this case. When the generator has a full running condition, then we again implement that. So this is the only difference between the thermal power plant and these pumped storage are gas power plant, which we required at the when we require more power during peak hours condition. So, what is the role of generator protection? So, during an internal fault, this is the same concept. The formula will also be same for the same make relays. Only this generator protection relay, if you are using generator protection relay, then it has many other protections also. Only difference. Otherwise, the formula will be same for the same make relay transformer and generator mostly. So differential protection relay operate when the current at two ends either differ mismatch by more than threshold value. This is the main concept in all differential. Not only this generator, but transformer and also light differential protection. So this is also same. The only difference is this NGR. That is what we have consumed and detected the whole condition. So all other things is almost same. So we will not go to detail in this case. If you have any question, then you can ask. So there are two differential schemes: high impedance differential protection scheme, low impedance differential protection scheme. That is also explained yesterday. Just have a quick overview as Sumalai already explained it very well, so I don't think there is anything left in this to explain. So here also he explained the conditions. In high impedance scheme, all the CT ratios should be same. In this, only pickup setting is there. So earlier we mostly using this protection when the numerical relays were not available. Then this protection was predominantly used in the many places because it is easy to set and understand. So stabilizing resistor and everything you have learned yesterday, how to calculate that resistance, operating on current balance principle, Like if there is any unbalance, it will flow through. That is the differential concept that is applicable to low impedance and high impedance both. But the method of detection is different. It is voltage based, that is current based. So much suitable for generator motor because due to this NGR, this can also detect the uh, uh, current, unbalanced current, and the setting is low. So during a cold condition, it may detect easily compared to the low impedance protection. So here, what are the requirements? It is equal CT ratio, low CT secondary winding resistance, adequate knee point voltage output from CTs, low lead burdens. Because we have already high burden resistance in this, so when it is injected through CT, so CT may be compatible for handling so much load. So for that we require higher knee point voltage. So otherwise, what happened during the fault condition, the CT may blast if it is not having capacity to handle so much voltage. So what it create when fault condition, CT current will be injected through this high impedance circuit. So if a current is injected, that is why metrocell coil is there to protect that. But still, the resistance, due to resistance, there may have a sudden voltage jump. So it may damage the CT if it is not properly coordinated with the requirement.
How you verify microseal when it's still okay or not, because we just leave it there.
Yeah, so
So how
so
you
it is a recommended whatever relay manufacturer. If you go through the manual, they recommend, you can find easily how much resistance it should be there, and based on that, if every answer is in the manual of the relay, whatever relay you have, just go through the manual, you will find everything. So they always recommend how much CT burden requirement, how much resistance you have to use, everything is in manual. So whatever relay we are using, if we want to find this answer, there is no standard answer of it. So I will tell you this one and this will be applicable to all. No, this is not like that. It is depend on the relay manufacturer recommendation, how they are detecting, and they will advise the CT requirement also according to that relay requirement. Any manual you will open that. I think first, second chapter, it all detail is there. This is not a standard.
How do you decide to use high or low impedance differential?
So, generally, uh, since when the numerical relays are there, so we are not using high impedance differential. Why? With a high impedance differential, only the differential protection is there, but we do not have much analysis. Even if you are using high impedance differential through the numerical relay, still they do not have much to explain what happened actually during the fault condition, because it can tell only the difference current. While you are using the low impedance differential, then each phase current, what are the waveform, everything will be available in the phase wise. So we want that all the fault should be analyzed very effectively. So that is why we move to the low impedance differential than high impedance differential. You will not find much high impedance differential protection anywhere now. Only we are using REF, and why we are using REF, yesterday he has already explained very well. So mostly we are not using high impedance differential now. So it is easy, but there are lot of things which is making it more complex, like CT burden also, because earlier electromechanical relays were there, so all the CT manufacturer were making CT according to that burden requirement. Now mostly the numerical relays are there, so burden requirement is not much. So if you ask, please provide the knee point voltage so much according to handling so much load, so the cost of CT will also be increased. So that is why mostly this high impedance differential protection is not in anywhere. So if it is a older plant, then you may find it. Otherwise, I have not seen that new plant they are implementing this, because we want better analysis. Our priority is better analysis first. So that can be done in the low impedance protection. Every detail you can find out how much harmonic current in which phase, which CT saturated, that all condition you can find in the low impedance. While in this you cannot find anything. What else? Here the next line it is there. Three winding differential protection scheme become more complex than low impedance due to these requirements. And like REF, the setting recommended is 10 to 20%. Relay operate time should be less. Ensure the proper value of stabilizing register. So it should be properly calculated as per the relay manufacturer recommendation and set accordingly. So MetroSil conditions is based on how much current you have selected, how much voltage it is. It will be at terminal of MetroSil normal voltage requirement. And low impedance. Low impedance. It is complex because of configuration and all these things. Higher cost compared to high impedance scheme. In high impedance scheme, you can use a simple overcurrent relay as well for this differential scheme. So that is actually the overcurrent relay. So you are injecting 0.1 ampere current and a relay is operating. That's it. But while in differential low impedance differential, the it is properly the six current channels required. If it is a two winding, and it also having different modules in that, so it is costlier than compared to high impedance. Setting are more complex, so if we want to have a better analysis, then obviously the setting and slope, these all things are required. The scheme is also called percentage differential scheme. Percentage differential scheme is for this restraining feature. The relay which have restrained wire, that is called percentage differentials. External fault, high restraint current. So like in this condition, we have option to compensate CT saturation, external fault condition with different slope and detection method, while in high impedance case it is not available. So in this high restraint current for the external fault, low restraint current for the internal fault, you can see from the scope here, low restraint current while going for true fault, then restraint current is higher. So so these feature, while in the high impedance differential there is no such protection. If there is a CT saturation case, relay will maloperate. So these all things are for older relays earlier, and now this low impedance differential scheme is for what we discussed today. So here for generator differential we have some overview, setting of overview. You can see CTPT ratio, what you have to enter before testing the relays. So system data. So in generator protection, not only differential generator differential protection is there. There are many more protection. Not only 9, more than this. It has shown only 9 here. Depend on the plant size, we have different protection, and we can enable as per the requirement. This is the generator differential protection. You can see the first slope is 0 to 20%, and this setting is from 1 to 5 IM, and second slope is 20 to 150%. So there is only one slope in this case. So this is how we connect the relay. This is the actual setting when you do. So sometimes you will find the settings in PU, sometimes in ampere. Here you can see the setting is in ampere, not in per unit. Why it is? So here also they can write the PU. In transformer, mostly you will find it in per unit, not in ampere. Why it is so? Yes. Yeah, because there is a different voltage level, different current rating. So from the per unit we can calculate for each winding. While in generator both are same, so that is why it is written in the current. So we can convert this also in PU. As you can see, the rating is 5 ampere, so we divided it in 5. Then the setting is a 0.1 PU. Turn point is a 7.5 ampere, so we divided it by 5, so it is 1.5. So even the differential measurement also will be in per unit as well as transformer differential, the restraint current and differential current measured in per unit, while in generator protection you will be finding it in ampere. So whatever the unit is, the calculation will be same. If either it is a per unit or it is ampere, the calculation method will not change. So you have to follow the same. Testing. Now, few more points which verifying elimination of zero sequence current. So this is the most complex thing when you are testing transformer differential protection. So what happen when how you will verify the zero sequence elimination is active or not? Generally, when it is star winding, then zero sequence elimination is required. Because if it is grounded, then definitely the current will flow through ground, and due to that, relay differential relay will not operate. Suppose you want to verify this zero sequence current elimination is active or not, you just inject current in all three winding with 0 degree, same phase current. Then suppose you have injected 1 ampere in each winding, and setting is a 0.2, then relay should operate definitely. But if zero sequence elimination is active, then it will not trip. Differential relay will not trip even you are injecting 1 ampere. How you can understand this? So if you know how to calculate zero sequence current from phase current, you just put that formula. Then you will find that if we will add all phasor current, then the sum will be the zero sequence current. No positive negative sequence current. So as he explained yesterday, was the pickup current. So suppose the differential setting is 0.3. This was the pickup value, right? Yesterday's we take the reference of yesterday's setting only, so that there should not be any difference. Then if we want to and the rated current was 0.73, rated current. I am talking about secondary current. It is 0.73. It might be different also. It is just for calculation purpose. Maybe I do not remember, then it will be wrong. Then what will be the pickup current of the HV side? It will be 0.3 into 0.73. Correct?
Yes.
So
0.
whatever value is there.
0.219.
No. 0.219. Yeah, this will be the pickup current. So if we inject, then the relay will trip. This will work only when it is a delta a three-phase current we are injecting. Three-phase balance current. 0, 240, 140. Symmetric current we are injecting. Suppose if we are injecting the single phase current, then this current maybe anything. There are four possibilities. So I will explain in the coming slide. So the single phase pickup current will be different than three phase pickup current. So because of this internal compensation. So why this zero sequence current elimination is necessary? So actually the this zero sequence current is not the differential current. It is coming from the ground, so it is an external current. So that is why it is creating a problem in the differential relay. That is why we eliminate it. So in this case, if we are injecting, suppose for calculation 0.3 ampere, then what may happen? The relay may not trip at 0.3. So suppose the pickup current is not a 0.21, it is a 0.3. Then the relay may trip at 0.45 or 0.51. So we can understand the what compensation is in each winding. Based on that, we during the slope calculation, we compensate in the current injection. For three phase slope testing, nothing is required because in that case zero sequence current will not be there, so no need to do anything. But when you are selecting, we need to check the differential relay for the single phase condition also, because mostly the single phase to ground what happened. So in that case, how relay is behaving. So in that case, we should consider this zero current elimination. So how we can do that? Here we have balance current. So this is the basic measurement when we do the stability test. This is phase compensation 0, 180 degree. If it is a star connection, if anything different, then you have to. If it is a YD1 or YD11, yeah, DY11. So based on that, we have to set the this balance current. This we already learned. Here. So what the factor what is if we have a star delta winding, then we can see that if 1:1 ratio, then the square root factor implemented here. So whatever we inject here, it will be divided by √3 in the winding. If we inject the balance current, then it will be shifted by -30 degree. In this case, maybe +30 degree, depend on the winding connection it has. Okay, so zero sequence compensation will be after this, right? So maybe after break. I'm sorry.
2 minutes is there if you
Yeah,
person.
okay. So just do this and we'll learn detail of the zero sequence
Okay.
compensation.
Okay.
So here the square root factor is computed. Now if we are injecting 1 ampere in one winding, this will be the it will be injected in two phase while we are from injecting through this. That is why if you see in the software when we are doing the single phase differential testing, in the start side one current will be there in the suppose we have R winding we are injecting, then you will see in delta side there will be two current to balance this one due to this. So this is how we calculate the zero sequence compensation. So first we will take the three phase pickup. So we know that what is the actual setting and what actual pickup current, and then we take the single phase injection and we note down what is the pickup current in this case, and this single phase current is divided by three phase current. So the ratio will be these four only. All the cases, only these four condition will be there. So in any differential relay, if you will test, then so either you will find the factor is 1. If it is a delta winding, then the three phase and single phase pickup will be same. If it is a zero sequence elimination in a star winding, then you will find this condition. Yeah. So we will set us in software YD void. D is for eliminating a zero sequence component. So if it is a YD setting, then the ratio will be 1.732, and YD plus 0, so this ratio will be 1.098. In most in all cases only these four factor will be there. So based on that we can choose our vector compensation. This vector compensation is not the transformer vector. This is compensation for zero current, sequence current elimination. So maybe when we demonstrate tomorrow, then we can have this. We can do it in detail. Maybe we can change the different vector group and know about all these cases. Okay. Okay. So we will continue after.